In this video, we're going to look at heating curves, and we are going to look at heating curves mostly for one reason, which is just to remind you that we have different equations to use relating heat to temperature change or relating heat to a phase change. So a common problem that comes up in this section is draw a heating curve for water from negative 25 degrees Celsius to 120 degrees Celsius, or calculate the amount of heat needed to go from water at minus 25 degrees Celsius to water at 120 degrees Celsius. And very, very often, students will immediately just use Q equals MC delta T and make the temperature change from negative 25 to 120. So that's what 145 degree temperature change. But this doesn't work because of the phase changes. So you have to remember the things that we've talked about with phase changes already, primarily that there's no temperature change during a phase change, but we absolutely have to either put in a bunch of energy to make that phase change happen, or we will get a bunch of energy out when that phase change happens. So we're going to plot this for water. You could do it for any substance as long as you have all of the constants, including what temperature it freezes and boils at. So water freezes at 0 degrees Celsius, boils at 100 degrees Celsius. So if we're going negative 25 to 120, we are starting as a solid, turning it into a liquid, and turning it into a gas. So what you will see for this kind of plot is that we put temperature on the y-axis and heat added on the x-axis. So the heat added, we're just making whatever our arbitrary, our 0 point is wherever we start, and then we're going to add heat to it. So that's what we're plotting on the x-axis. So for water, if I want to go through this entire temperature range, when I start at negative 25 degrees, I have a solid, and I will have to warm that solid up to its melting point before I can melt it. So the first section, the first thing I'm going to do is warm up the ice from negative 25 to 0. And that has a temperature change. It's going to be a solid the entire time. So the amount of heat that takes, it will depend on the mass and the specific heat capacity. So I will need, for one of the constants I will need is the specific heat capacity for ice, because I will have to use that specific heat capacity. Now, once I have it at 0 degrees, I'm going to melt it. And the amount of heat that it takes to melt the ice, it depends on the enthalpy of fusion, which you need the number of moles for that. So I need number of moles times enthalpy of fusion. There's no temperature change. All of the heat that I put in will go toward turning it into liquid water at 0 degrees Celsius. So this section of my heating curve will be completely flat. There's no change in temperature, but I am adding heat for this to happen. Now I have a liquid. So now I can warm up the liquid until I get to the boiling point. So I'm going to warm my liquid from 0 to 100, and I have a 100 degree temperature change. I can use Q equals MC delta T. I'm going to need the specific heat capacity for liquid water. That's just the one that we happen to use the most. And my temperature will change as I add all of this heat. This is my third section here. Now I have water at 100 degrees. I need to turn it into steam at 100 degrees. So enthalpy of vaporization. I'm at the correct temperature. I need to do this phase change. No temperature change. All of the heat that's put in goes toward doing the state conversion. So Q equals N times the enthalpy of vaporization. And now I have a gas that is 100 degrees, and I want to take this to 120. So I have another 20 degrees that I need to heat up my gaseous water, which means I'll have a delta T, right? But I need the specific heat capacity for gaseous water. So if you're doing a heating curve that goes from below the freezing point to above the boiling point of any substance, you will have these 5 sections, right? There's a section where you're just heating up the solid, a section where you melt it, heat up the liquid, boil it, heat up the gas. You have to do each one separately because the specific heat capacities of the different substances are different, and because there is no temperature change during a phase change.